Thank you very much, Matthias. The presentation from Arn was great. I really enjoyed it. It's so fun to see what people are doing these days. I'm just going to hide the UI here and get going. Okay, thank you very much, Matthias, and the ICE team for allowing me the chance to speak to folks about probably a bit of a different set of topics from what most of the folks on the session are going to be thinking about. But hopefully I'll give you a bit of a view into a different range of 3D and how some of us use and view 3D in the world. I'm going to be talking about synthetic data for AI worlds, but what I'm really talking about is AI being applied in the world around us, not so much using AI to build virtual worlds for visualization and entertainment uses, but more how we actually are using the inverse, which is 3D and other simulation technologies, to supply data for training artificial intelligence. So I'm Chris Andrews. I am the COO and head of product at a seed-funded startup called Rendered AI. My background, though, is fairly deep and diverse. I actually taught the first GIS classes at my university, having taught myself geographic information systems. My background is actually in geology and biology, actually specifically ecology and evolutionary biology. But basically GIS and programming got me my first jobs. I ended up going into some small product companies for a while, and then I was in enterprise integration, and from there I bridged over into product management, which is where I initially met Pascal Mueller, one of the folks that Matthias worked with very closely with procedural. And then at Autodesk, I worked on Project Galileo, which became a product called InfraWorks, which is out there and is used by tens of thousands of engineers. I actually did a brief stint in molecular visualization in Autodesk. I then, as Matthias said earlier, went over to Esri, and I spent about 7 years there leading 3D and the AEC GIS integration, including helping get the Autodesk partnership started. I joined Rendered because it kind of brings together my background in geospatial, 3D simulation, and data disparate or data difficult domains. Okay, go forward. All right, so first I'm going to just give a little bit of a talk about the issue that we're encountering with data in the world around us. So one of the things that I've learned throughout my career is that the end user application in real world domains like defense and utilities, local government, urban planning, you name it, the end user application really drives what data is needed for addressing or answering questions, addressing problems in those specific domains. The company that I'm at now helps customers actually create data in order to train algorithms to solve problems in a variety of domains. But I would simply say that it doesn't matter whether we're talking about real data collection or synthetic data generation, or even some of the entertainment data creation, such as what Arn was showing. The data that ends up being created has to be very specific for the end purpose. In the kind of real world domains, what we're seeing today is that everything around us is being captured in 2D and 3D. And I have a simple little Arduino camera there as an example, but we can pretty much be sure that in retail, in utilities, in local government and security and all kinds of domains, we're basically capturing everything with cameras today. As one example, the number of Earth observation satellites that were being put up in this decade was projected to grow by about 50 times between 2020 and 2030. And that is just satellites that are collecting remote sensing data of the Earth, so it has nothing to do with all the sensors down on the Earth as well. And then if you also consider the fact that those satellites are in some cases having more sensors than ever before, or the ability to collect larger larger or higher resolution images than ever before. And what you can say is the amount of data that is being collected around us is really exploding. Actually, and as you saw with what Arne was showing, people are also now generating data, which is also phenomenal. One of the conclusions, though, that we can, observations we can make is that most of the data being captured today is unstructured, meaning it's pixels or other data that really has no other intrinsic information aside from the context and the spatial information about the pixels themselves. It's unlabeled, meaning that humans have not looked at it or machines have not looked at the data to identify what each pixel actually represents or where each object is in the pixel. And so that means that most of this data that we're collecting today is not ready for use in training artificial intelligence or for use in being analyzed by artificial intelligence. We're trying to process all the data to try to address some really significant issues that are going on around us, like the need to support population shifts, the need to support a transition to cleaner energy, need to support transition to safer roads and safer vehicle driving patterns. So we're trying to process all this data so that we can arrive at actionable conclusions. And we're assuming that 3D machine learning and artificial intelligence are essential tools to help us process all this data. So I'm going to switch over a little bit and actually talk about why I am focused on synthetic data these days. So as we're trying to process all that data, I already hinted at the fact that most of the data out there is unstructured and not ready to be used. What we see very commonly is that companies who are trying to deploy new algorithms to attempt to analyze data as part of their business model or their operational model. So this could be, for example, a city trying to install traffic and pedestrian monitoring cameras to make sure that the pedestrians are safe when lights are changed. These types of implementations frequently run into some very common issues. On one hand, what we most often think about is the issues on the right here, which is that real data captured with real sensors tends to only capture the stuff that happens commonly. So real data sets are often biased against or away from rare objects and scenarios. Similarly, when you actually take real data and then you have to actually label it, so you actually have to add metadata into it to enable an algorithm to be trained to understand what's in the pixels, then typically most of the ways that we actually label data today are imprecise and incomplete and also expensive. So when it comes to training algorithm performance, we often run into bias and accuracy issues associated with the data itself and then the labeling of the data. On the other side, we also run into customers who are finding that real data set acquisition is super expensive, and it may even be impossible in some cases to acquire and label certain types of data. In one case, for example, in the European market, is data with people's faces tends to be very difficult to obtain because of the need to get release of personally identifiable information, which makes it extremely expensive and difficult to acquire human facial data. In some cases as well, such as when you're putting up a new satellite and you want to start figuring out how you're going to actually process the data from the satellite, you can't actually get data from it till it's up in the sky. And so you actually can't innovate without having until that data starts streaming down from satellite. So in that case, we run into issues where AI implementation can be obstructed because of cost and delays in time to market. Synthetic data has the opportunity to actually solve this AI problem. Synthetic data is engineered or simulated data that AI interprets as if it's real data. And we're seeing quite a bit of synthetic data is actually well established in the industry today. Some of the major market analyst groups like Gartner and Cole and others have done studies on the availability or the access to generation of synthetic data. There's synthetic data that's used in the text side of the data world for things like simulating banking records or payroll records. And then we're on the computer vision side of the world, obviously. We build a PaaS and a developer framework for helping others generate synthetic computer vision data. When I talk about synthetic data, I am specifically talking about generating or simulating sensor data as if it was captured by a real physical sensor. So there is a little bit of confusion these days with synthetic data coming out of, say, diffusion models, and I'll address that a little bit more in a minute. But when we talk about generating synthetic data or helping customers generate synthetic data with rendered AI, what we're talking about is effectively simulating the pixels in an image as if they had been captured using physical systems with specific sensor parameters and scenarios that could have been captured in the real world. And almost all of the imagery that is in my presentation is from rendered. So you'll see several examples of what that actually means. Okay, today's AI workflow typically relies on finding or acquiring data. What we often find is that data scientists are essentially handed data sets, they're dumped in their lap, and they're told, do something with this, solve some business problem with this, with the data that we're giving you. In this case, what ends up happening is you kind of are stuck with what you get. Data scientists have become very good at manipulating data sets to try to squeeze every last performance percentage out of an existing data set. But at the end of the day, if you're looking for purple elephants and you don't have any purple elephants in your data set, then you're not going to be able to train an algorithm to find purple elephants if you're only using the real data set that you're handed. What we've observed is that tomorrow's AI workflow really incorporates synthetic data. Synthetic data gives you this interesting opportunity to actually create the data that could potentially help you train your algorithm, do the training, test it, and then compare data sets to see if experimentally if your synthetic data that you're generating is helping improve training. And then if not, you can even go back in and create more data. And typically what we're seeing is that this actually helps customers arrive at successful algorithms. It tends to be inexpensive. The labeling is 100% accurate. So when you're using synthetic data, you can actually remove some of the human labeling effort. You can still use real data sets when you're using, in fact, most of our customers do use real data sets alongside synthetic data. And then you can specifically use synthetic data to design for edge or impossible cases. We've even had customers use our platform to generate data sets that were truly impossible, as in unrealistic or unnatural, to demonstrate that an algorithm would fail predictably. Classically, what we've seen is that many folks have approached the idea of generating synthetic data as if they can just go grab a renderer off the web, maybe Unreal or Unity or even Blender or some other simulator. They'll set up some project where they'll generate a synthetic data set or two, and then they'll go off and think that they can train a bunch of AI models with that. It doesn't work. We've heard this from customers over and over. In fact, in many cases, we've encountered customers who've tried this approach, and they're dissatisfied with the idea of synthetic data or skeptical because they took this approach and it didn't work. What we tend to see is that the process for generating synthetic data needs to be a fair bit more iterative and empirical. So you build your world, maybe even using some of the techniques such as what Arne showed earlier. You then deploy your world with a simulator to a compute platform in some way where you can use it to generate thousands of images over and over and over. And then you have to send those images to a data scientist who will process the images, attempt to actually train a model, do a quality assessment on the images, and if needed, will feed back requests or requirements back to what we call a synthetic data engineering team to basically generate, update the simulation and enable the data scientist to generate more data. In many cases, a data scientist with rendered is able to actually do a lot of data reconfiguration themselves without having to touch 3D or simulation technology. But the initial simulator setup is often done by someone who we refer to as a synthetic data engineer. in some cases, we may play the role of the synthetic data engineers and actually help our customers get started. But through this iterative workflow, we have seen customers find and achieve success with synthetic data. So that brings me to one interesting item, which is Matthias pointed out that there are sometimes some earlier career folks in this event, and one thing that we have seen is that there is an evolving need for a role that we refer to as the synthetic data engineer, who actually might use many of the techniques that are applied in film and game market, but then bring them over and start applying them to generating simulations and environments for real-world domains to simulate real-world data. We employ a couple folks who come out of the film and game market, and what we find is that there's an interesting kind of intersection of reality capture, modeling technology, simulation, and other technologies that ends up being highly useful when you need somebody to basically be in this synthetic data engineer role. The steps for generating synthetic data typically involve characterizing scenarios, building a world, modeling a sensor, designing the specific annotation needed, running jobs, and then post-processing data sets, and sometimes characterizing data sets. With rendered AI, we provide a platform where we're trying to make many of these steps easier for anybody to do. There are still different phases of the process that may require deeper domain specialties, such as in the synthetic data engineering piece. One thing that we have had quite a few questions over is, what about generative AI? Is Stable Diffusion going to make the need for rendered to go away? And the reality is no. What we see is that most of our customers need fairly precise, hyper-specific data for training algorithms to solve and address their issues. As I said in one of my first slides, the data, the problem being solved, drives the data that is required. And when you are trying to train for running algorithms against very specific sensor captured data, you need to really model the behavior of those sensors. In some cases as well, when it comes to things like radar or hyperspectral imagery, there is not enough of that imagery in the public domain to train big diffusion models today. So you, in many cases today and for a long time to come, you will not be able to get diffusion models that could generate certain types of data. We do see generative AI as playing into the world building and background creation components of synthetic data, and we have some active experiments working with generative AI through Shutterstock's tool and through some other things going on today. Of course, I suspect most of the folks on this call have heard of this role called a prompt engineer, and it does not mean a speedy engineer, right? It means somebody who actually can understand a problem, formulate a description of an outcome, pass it through a large model of some kind, and then get a desired result. Interestingly, watching Arn, he has some facets of prompt engineering in the way that he works with Comfy UI, and what I find observing folks more and more is that the specificity of the prompting is really going to need to be driven by the specificity of the problem that you're trying to solve, the data you're trying to get. And there will be some people good at specifying text output through prompting, and there will be other people who are really good at specifying different types of visual output through prompting. It will still take some domain expertise to understand what it is you're prompting for and why. We do run into some common gaps when we're introducing customers to the idea of synthetic data. There can often be a hyper focus on existing data sets or the limitations of acquiring existing data. Most data scientists aren't sensor experts, so they don't really understand what it means to have a physically accurate image based upon the sensor they're working with. We have a lot of concern from customers or prospects about good data. Ironically, in some cases, customers really need good, bad data. If a customer needs data that will predictably fail an algorithm, then they're actually looking for bad data in some cases. And you can use rendered AI and other tools to generate synthetic data that's bad in a predictable or desired way. There is some concern about one-off data sets versus investment in data. One of the most amusing things that I see, and I learned this the hard way when I transitioned in Autodesk from infrastructure into the film and game group, is that most people think that they see really good and that they can look at a remote sensing image and know whether it's a real image or a fake image. In reality, I learned a ton more about visualization when I moved over into film and game briefly at Autodesk, and I was shocked to really learn that the way that I use the word visualization in the infrastructure domain was very different from the way that somebody like Matthias thinks about, or Arn thinks about visualization. And that's maybe another way where some of the fear that Arn talked about of AI taking over artists' jobs is not, it's not a real concern, because the expertise required to know what you're getting out of it is still going to be something that's sought after for a long time. I don't think it's going to be possible to have a machine replace that kind of visualization expertise anytime soon. There is also some confusion over generative versus simulation techniques that we're seeing. But the biggest question, or the biggest hurdle that we typically encounter, is that customers rarely stop to ask themselves what the ideal data set would be that would address their business problem. Customers, back to what I said about data scientists earlier, most data scientists are handed data sets. So they've never paused to think about, well, what would be the best data set to try to solve this problem? And so what we see is that synthetic data generation tends to be a quite empirical process. First, you have to really, we work with our customers to help them identify what specific problem they're trying to address. This can be quite subtle. In one case, with a transportation customer looking at vehicle equipment, they came to us with one ask, and then much later came to us and described that, oh, they were actually looking for a different conclusion. So they originally came to us asking if we could help them identify something, but then later they came back and told us that, well, they actually didn't have that many problems identifying it before. Their issue was reducing false positives. So you really need to identify what your problem is, not just from a physical identification of what's in an image perspective, but you also need to understand that within the context of your business problem. From there, you might start out by describing or ideating about what the ideal data set might be. And most data scientists have never paused to think about that before. That description plus information from the problem domain can be used to go into what we call a synthetic data channel or simulation that can be used to generate data. From there, once you generate data, you can ask, can I train for what I was looking for? And you can test it, test inference, and then typically your first tries are not going to work as well as you might have thought. So you do some analysis on what went into it, and then you basically refine data generation, and until you arrive at a training level that you think is okay. And then from there, you continue to refine until you improve it to the level where you need it. One of the biggest challenges that our customers face is that they're not ever going to be arriving at a fixed destination when it comes to training algorithms to solve business problems. The business problems underneath the algorithms are always going to be changing, shifting, whether that's because you need higher performance next year, or whether that's because you need to find new things that you didn't think you were going to be looking for. But the problems that you're addressing in your organization or your customers' organizations are always going to be shifting. It's a moving target. Okay, so I'm going to move a little bit over to talking about 3D and some of the ways that I think about 3D. There are one of the things that I've learned shifting domains from infrastructure to life sciences to film and game and others is that everybody uses the term 3D, but they never ever mean the same thing. Okay, so one thing that we run into is customers really expect to be able to reuse data across applications. For example, a customer might see a really cool looking house model in the latest, the latest action movie that is up online. They may even know that that house model was produced by a certain firm and that it's listed online somewhere for sale after the movie's over. And they may say, hey, great, we can go use that house model to do something different, like maybe a thermal analysis of residential occupation of the house. In reality, that is really, really difficult. It typically doesn't work that way, especially when pulling assets out of the film and game world for use in real world domains. What we often see is that shortcuts taken to make something look visually interesting for a film or game often are not acceptable for use in an analysis in a real world domain. And likewise, the resolution of assets required for a lot of real world domain analysis don't lend themselves to the visual quality required for specific film and game sequences. So our users often end up frustrated. They'll collect data and expect different data sets to work together, but mixed resolution leads to imprecision that they want to control for. They may not have the right ownership or chain of custody for data, meaning they can't trust it. The time scale of data might not work for a particular problem set. This is really true in things like construction and urban planning. And then missing coverage leads to additional collection or creation. There's a lot of entrance into like geospatial and real world data collection and usage will assume that there's all this data out there that can be used, but often the existing data sets that are kind of publicly available online suffer from several of these issues. And unfortunately, many of these issues are simply not going to go away. And that's really because your 3D and my 3D, each of our customers' 3D problems are not the same. Back to problem drives the data. What we see is the problem will drive the specific resolution of data, the provenance of the data required, the vintage of the data required, and even the coverage of data required. One of the things that folks like myself have worked on over time, and Matthias and others who've been in the 3D software industry, is kind of attempting to draw format out of the question. And some of this comes from a talk I gave at GTC recently, and you'll explain, or I'll explain how this is relevant to NVIDIA and GTC. Ultimately, what happens is we become these trusted advisors that need to help our customers understand what data will be required to solve the problems or address the problems that they're trying to solve. We, as trusted advisors, need to avoid hype, know the problems, understand the domains, and then recommend repeatable solutions. And one thing I really love about the presentation that Arne gave is for his domain, he's really articulating a very interesting experience for repeating a solution to quickly get at assets that can be used as context in film and game, or as starter assets for further development. Arne was giving us a presentation as somebody who is a trusted advisor to his end customers in that film domain, which is great. Standards become critical when you want to try to exchange data especially across industries or domains. Standards tend to reduce workflow friction, optimize reuse, and enable future recoverability of data sets. One of the interesting things that a lot of folks might not realize is that OpenUSD was originally started by Pixar with the help of Autodesk and others to try to drive better exchange of data within the film domain for doing things like distributed rendering in the early cloud. And it's really, really great to see that USD has evolved to be more of a generic 3D interchange standard across the industry. That said, it does not solve all problems. At GTC, there were quite a few people who asked questions about using OpenUSD for non-visible light domains, and it's really just starting out at baby steps there. And then for some things like geospatial, you may end up needing to move over to other standards like 3D tiles or I3S from Esri, which I worked on for a while, and which are both Open Geospatial Consortium standards. And there are many, many other standards out there. But one important thing that we all are trying to do is help our customers with some of those reuse issues, and standards are a critical piece of that story. For rendered, we actually do use OpenUSD and Omniverse to help us accelerate the ability to reuse assets across different simulations. And so this is just a really quick demo of somebody grabbing an asset online, basically doing a little bit of prep, and then using it in a synthetic data channel inside the rendered UI. And so, so we typically rely on open specifications and open technologies like Omniverse to basically accelerate and magnify our ability to do cool things as a small company. What we are seeing is that some of these tools have the opportunity to help standardize a pipeline that can make it easier for our customers to generate more, to create more synthetic data channels. Some of these technologies are increasingly becoming better and better at being really industry agnostic. And then we actually do see a lot of movement around standards and metadata that help us reuse data and even generate output data for training that are more useful to our customers. So any of you out there can actually play around a little bit with rendered AI. We actually do have a channel for NVIDIA Omniverse that allows you to create these graphs that allow you to drive synthetic data runs. What you'll see if you try our demo is that these funny things are the standard replicator demos. Replicator is an NVIDIA Omniverse kit extension that is specifically for synthetic data generation. You can run it from within rendered and up on the cloud, and then you can create graphs which describe synthetic data runs. You can kick off runs, download data sets, and even use some of our other tools up in the platform. As I said, the examples that we have are, if you were somebody who set up Omniverse Replicator, let's say on a your own server or local machine, you'd find these tutorials to be, or these examples to be very familiar, as they're straight out of the tutorials. We have added some things like the ability to display annotation. We also have an experiment up online where you can use Omniverse in rendered AI along with NVIDIA Tau to demonstrate a transfer learning experiment. Okay, so you can check this out up at render.ai, and you can sign up for a free account. Choose the NVIDIA Omniverse little card in the sample gallery and play around a little bit. And then there is a YouTube video if you screenshot this, which walks through the Tau demo as well. So thank you very much for your time. I could show a little bit of the interface. I think we're running a little bit short on time. I guess let me quickly go over to our website, and I'll show you exactly how to access rendered. So this is the rendered website. You can see on just about every page there's a free trial or a sign-in link. If you go to our blog page, there are a bunch of pieces of content about all kinds of different applications of synthetic data that we've done. I think there's about 80 different blogs up here. And you can see a lot of our stuff is focused more on the remote sensing domain. We have access to a few different simulators that have been well supported in the community for a while. We've had some great customers like Planet, and that's, like I said earlier, that's in alignment with kind of my background. If I sign in, I'm just going to click over here. You can find the sample gallery right here up on the upper left in the kind of the landing page on our interface, and you can see we have some different samples that are up there. We've had folks ask us about warehouses and could they randomize boxes. We've we've built a couple simpler channels for demonstrating how you can just drop random things in boxes. This shows toys, but we also have an example of dropping fruit and in baskets. And then there are many other different types of applications out here, some with quite complex atmospheres and other effects in the synthetic data that's generated. If I actually go into one of these, what you'll see is, I'll bounce into the Omniverse example. So it's a fairly straightforward web interface that's really accessible to data scientists. The data scientists can come in here and pretty easily drag and drop in new items, so new assets from the scene or objects to be generated. They can drag them right in here. You can even add your own assets into custom volumes in rendered. Then you basically set up this configuration, which describes a data run. You can kick off jobs. You can see some jobs that have already been run here just in this demo workspace. And then you get data sets. And the data sets are, these are kind of goofy because they're this tutorial data set, but the data sets have, as you can see, annotation information, both 3D and 2D bounding boxes. Actually, in this channel, there are no 3D bounding boxes, but there's some image segmentation, and you can get the different image masks. So then this is ultimately what rendered is all about, is helping customers generate data with this information to meet the scenarios they need to train algorithms. So that's it. I guess we have a couple minutes for questions if anybody has any questions.
Cool, but let's get started. So there's a question from Mike Shawbrook, and he has a kind of interesting question. Are there specific AI projects dedicated to prompt engineering, so kind of to learning to prompt engineer itself? Or so kind of, in other words, is AI being taught to prompt AI? So I would assume that's exactly where the human notion actually has to come in, because that's not yet possible, luckily, right?
Well, actually, I have seen I've seen a few different academic articles and also some other less than academic but still technically serious articles coming out of some of the big LLM companies, for example, where they are, in some cases, they're finding that it is actually possible to get better prompts by using prompts created out of an LLM. And I believe some of the reason for that is because you can provide the LLM, like ChatGPT or Google Gemini, with context to try to push it toward a certain chain of thought or line of reasoning. And then once you start asking questions of that, you get a fairly specific result that's filtered through this statistical space of information that the LLM is drawing from, based upon these contextual items you've given it. So in a way, like we're just removing the human to a more sophisticated level around kind of prompting the prompt chain. But it is possible to get to drive prompts from output from an LLM. I've seen several articles about that. At the end of the day, though, it goes back to, you still need to be specialized in something to know what questions to ask. That's the problems that we are addressing or applying artificial intelligence to are generally human-caused problems. so it's typically going to be humans that understand the domain nuance of those problems. But yeah, it's certainly, that's an area of active research, as I understand it.
Yeah. No, definitely. And I mean, I would completely agree that there's much more coming in this realm, or even tools that may be able to support you in your prompting, or maybe in a couple of years even, like the whole what's the name, Neuralink of Elon Musk, right, where you might just, if you cannot verbalize something, you might just feel it, and the computer will be able to extract extract it and put it into words and images. That will happen in a couple of years, right? Which is crazy. But yeah, and also, I mean, the domain specialty, or let's say if you're looking at something that is as complex as, let's say, just a digital camera, especially if it has, let's say, capabilities that are both in the visible light spectrum and in the invisible, kind of, let's say, infrared at the same time, or because that's what they have to do. And that's also, so a couple of years back, I've been in a project where kind of all of these, like all of the spectral information was really a part of the issue. And if you have just 8-bit textures of a 3D model, it will not give you the full the correct specific spectral information of that this is a metallic surface, right, or this is a warm surface. So for example, that if a car has to detect if it's a lamppost or a person, and so that the car in worst case scenario doesn't drive into the object, but can literally distinguish between them. So that's so advanced that will probably take a long time for the machines to take over, right?
Yeah, and that goes back to what I said earlier about I briefly mentioned that for a lot of the non-visible spectrum domains, there just isn't enough data out there to train an algorithm to then generate data like that. We've seen a few attempts at using diffusion models to do things like generate synthetic aperture radar, which is if you've been paying attention to any of the popular press about remote sensing, what you can use synthetic aperture radar for is seeing at night. So you can get pictures of things through clouds or at nighttime. So it's useful for disasters and defense and intelligence uses, and even certain infrastructure use cases. There was a SAR image generated of the tanker crash into the bridge in Baltimore. And there just is not enough synthetic aperture radar out there to train a diffusion model. Those images are basically interferograms, and it's going to require a ton of data to train a model to be able to spit out and a physically accurate interferogram. And we are decades probably away from having that much data in the public domain to be able to train models.
Mm-hmm. I do have a question myself, because I'm also not getting one through the chat window here. So for rendered AI, how much or what goes into the decision or the reasoning why you're selling the raw data versus a trained model?
Oh, we don't. So let's see. That's more of a supply chain separation today. So if you go into like the reality capture industry, you will find folks like Nearmap or Vexel or others who are actually, they may even go beyond the trained model. So you can collect the data, you can train models on it, but then you can also extract information from data. And so what you see with some companies like that is they're moving all the way to extracting information from their collected data, and they've got their own model training workflows in-house. For rendered, where I could bring up a different slide that kind of shows our view of where we fit in the market. Our objective is to try to wrap a lot of the complexity of simulation and cloud setup and job management to allow kind of the middle and long tail of the market who wants to use computer vision to access data in order to train models. And so that's the market niche we're focused on. We actually have some experiments right now because of customer demand, kind of pulling us into doing more with model training. And what's come about is more customers asking if they can stay in the same platform and train models using data from the platform, but also data that they might upload. So that's been the original thesis of the product was to focus on the synthetic data generation itself, but we are getting pulled a bit more into the rest of the workflow.
Yeah, yeah. All right, let me quickly check if there's another question that has come in.
Yeah.
Not at the moment, but
okay.
You actually, you told me you need to run, right? So I would say I'll collect if there are more questions. I have some noted myself here, so I'll send them your way, and we'll manage that these answers are gonna be communicated through the Discord channel.
That's great. Thanks everyone for spending some time with me. So thanks for the opportunity to speak, Matthias.
It's been a pleasure. Thank you so much for all the insight and the inspiration. And yeah, I would say have a lovely day. And we're gonna take a 7-minute break.
All right. Take care.
All right. Bye bye. Thank you so much.